All right. So, good morning, everybody. So, what we have been talking about in the classes so far is electromagnetism. So, I've covered all of electromagnetism that is relevant for our course. The only thing that I haven't explained to you is how we get this wave equation and what are the solutions of this wave equation and what it tells us about the speed of light. So, I will do that today. Okay. But before I begin, are there any questions about any of the material that I've covered in any of the previous classes? Okay, so if you have any questions at any point, you please just unmute yourself and ask, okay? All right, so we have these equations of electromagnetism. And I know I write them down in every class. So you must be quite tired of seeing them again and again. But the reason I write them down in every class is that so that they can be burnt into your brain, right? When you see the same thing again and again, eventually you will remember what it is, right? So now what we want to talk about today, right, is electromagnetic waves. And electromagnetic waves or electromagnetic radiation, this is actually the single most important prediction of Maxwell's theory, right? Everything that you do in your daily lives depends on electromagnetic radiation. If you don't have electromagnetic radiation, you can't have light, right? That's the first thing. Light is electromagnetic radiation. So are radio waves. So is everything. Every process that is going on inside our body, outside our bodies, everywhere, electromagnetic. It is being done with light in some way or the other. So without light, we have nothing. We have no life, right? Not just in a literal sense, we don't have life without light, right? So how do we get electromagnetic waves, right? Now for electromagnetic waves, you get electromagnetic waves. What are they when we say that there are electromagnetic waves? We say, well, we know that there are electric fields in space, right? So for instance, I could have some region of space where there is an electric field that is decreasing like this, and then maybe it starts increasing again. Okay. So this sort of behavior, right, is what you would associate with a wave, right? And in this picture, it is important to keep in mind that I am drawing these vectors. So what do they represent? They represent an electric field which is, so you have some real line, right? X, let's say X axis. And what do these vectors represent? These vectors represent E of x, the vector E at the position x. So that means this green vector, this one over here, represents the vector field at this position, right? And so on for all the other vectors. So the arrows, they should not make you think that I'm drawing the electric field as being extended into space in that direction. It's a vector at that point, right? But it's not a vector in space, right? Now, so if you go just a little bit above the wire, the electric field might change in some way, right? So this is an electric field on a one-dimensional wire. Okay. Now, when you think of a wave, you have something that changes in as a function of position normally, right? So if I have this E of x, right, and I want to write this E of x as some function of position. So now let me say that I have some axis. Let me say this is my z axis. This will be my y axis. And if I want this to be the positive z axis, then I have to make the y axis in that direction so that x and y, they give me a right-handed coordinate system. So now the vector E of x, you can see at each point along this line x, where does this, which direction is this vector pointing in? Okay. The way I have drawn it, all of these vectors are pointing along the z-axis. So this is a vector which depends on x, right? How should I write it? Well, I'll write it as E naught. What is E naught? E naught is the amplitude, meaning the maximum value of this vector. And what is E naught? E naught will be something times z hat. It's a vector pointing in the z direction whose amplitude is E naught. Now, as I move along the x-axis, what happens? The vector becomes larger and smaller. So what should I do? I can write it like this: cosine of some constant times k. Right? So something like this. So if I say that this point is x is equal to 0, right? So as I go from left to right or to positive in x or negative x, what happens to the electric field? It is becoming weaker and weaker, and then stronger and then weaker and stronger, right? But now, and what is the meaning of this k, right? Why don't I just write it as cosine of x, right? Why do I have to put that k over there? So what is the meaning of this k? So this is very important to understand, not only for electromagnetism, but also for the next section, which is quantum mechanics. So let's say that I just have a function like this, a cosine k of x or cosine of x, right? So this is cosine of x. This is, now this is a wave, right? What would you say is the wavelength of this wave? The wavelength is given by the distance after which the wave repeats itself, right? So in this case, the wave repeats itself after from this point onwards over here, right? So these are the These are the 2 points between after which the wave repeats, right? So if I have cosine of x equal to 0, it is 1. What is the next value of x at which cosine is equal to 1? This is at 2 pi, right? So what is this length? This length is 2 pi. So I would say that the wavelength, right? If I think of this as a wave, the wavelength is lambda is equal to 2 pi, right? But now I want to change my wavelength, right? I want to, because wavelength can be anything, right? Waves can be, I can have long wavelengths, I can have short wavelengths, right? I can have waves that oscillate faster, that oscillate very slowly. So how do I change the wavelength? So if I want to change the wavelength, what do I do? I say something like, well, I have cosine of x, right? What do I do? Do I add something? If I add or subtract some parameter, what will this do? This will just shift the wave, right? So this is a translation by x naught. So if you put plus, that means you're translating backwards. If you put minus, that means you're translating forwards. That's why this is plus minus and this is minus plus. If I multiply by some parameter, this only changes the amplitude. Right? So I want to change the point at which the wave repeats. Right? How can I change that? I can just multiply it by some number. These are the possible things I can do, right? I'm just trying out all possibilities. One possibility is I can multiply this x by some number. Now what happens? Cosine kx at x is equal to 0 is what? It's 1. But then I want to find the next value of x at which it is 1. Right? So if cosine kx of kx is equal to 1, this means that kx has to be equal to what? Kx has to be equal to 2
0
pi.
plus 2n pi.
Right? Or 2n pi, right? N belongs to z. This is the integers. So the first value of k at which this pattern repeats is given by k is equal to, sorry, the first value of x is equal to 2 pi by k, right? This is the value of x at which the wave repeats, right? So what is this quantity? This quantity is the wavelength, right? This is one. So this is very important to understand. It's very simple, and many of you might already know this by heart. But if you don't know this by heart, or if you have seen it but you have not understood it, please understand it. This is very, very important. It's a very simple fact, but it's also a very important fact. Okay. So if I write something like cosine of k of x, what this describes is this describes an oscillation with wavelength lambda is equal to 2 pi by k. Okay. All right. So this is a wave. But now if you look at this wave, if you draw this, this pattern, right, what do you get? you get an oscillation, right? But this oscillation is frozen in time, right? So what does that mean? That means that, look, if you are an observer and you are standing at this point, location X, right? What will you see? You will see that the amplitude of the wave, and let's say the wave is an electric field. So I can see that you guys are turning your videos off one by one, and that's really annoying. So please turn your videos back on. Otherwise, I will end this class right now. Thank you. You can eat, you can drink, you can do whatever you want. I don't care. I need to be able to see your reactions to know that I'm doing something correctly. So if you are standing over here, you will always see the electric field to have this fixed value, right? So it's a frozen wave. The wave is not moving to the left or to the right. So how do I make the wave into something that is moving, right? Because this is our understanding of waves. When you go to the ocean or when you play with waves in water, you know, those waves are always moving. You have the ripples which move along, right? So how do you make the waves move? Well, you have to put something in here which depends on time, right? So we want moving waves. That means instead of cosine kx, we need to put something that is a function of time. So instead of writing cosine of x, I should write cosine of xt, where x of t is some function of time. Right? Another way to look at this is to say that you have an observer who is moving in the negative x direction with some velocity v naught with respect to the original observer, right? So this is the original observer O, and this is O prime. With respect to this observer, right? What does it seem? This O prime says that the wave is moving to the right with some velocity v naught, right? Right? So if I want to write down the expression for the wave, what is the expression for the wave in the O coordinate system? It is this. What about the expression for the wave in the O prime coordinate system? Now I have to change from x to x prime, right? When I change from x to x prime, what do I do? How do I go from x to x prime? Well, the simplest thing I can do is I can do a Galilean transformation, right? I can write x prime is equal to x minus v naught t. So what will the wave become as seen by the moving observer O prime? It would become cosine of k and x. I have, so this would mean that x is equal to x prime plus v naught t. So I think I'm making a sign error. I think there has to be a plus here. So this would be a minus. So according to x prime, cosine k of x becomes cosine of k times x prime minus v naught t. What is this expression? This is cosine of k x prime minus k times v naught t. This is the wave as seen by O prime. Now, what is the wavelength of this wave? The wavelength is going to be the wavelength has to satisfy the same condition. When I change x by the wavelength, the function should repeat. So this means that the wavelength is going to be what? It's going to be lambda is equal to 2 pi by k. Right? So the wavelength has not changed as seen by this observer. What about this quantity k times v? K times v naught is equal to 2 pi by lambda times v naught. Right? Now this is equal to 2 pi times v naught by lambda. V is the speed of the wave, lambda is the wavelength, right? Now, what is the relationship between the speed and the wavelength? If you take the speed and divide by the wavelength, you get the frequency, right? This is the frequency. And this quantity 2 pi times f is called the angular frequency, right? So what are the units of the frequency? The units of frequency is just T inverse. What about the units of angular frequency? It's equal to radians per unit time. Because 2 pi radians, right? 2 pi is equal to 360 degrees, right? 360 degrees is equal to 2 pi radians. So I can write down the expression for the wave. For a moving wave, it's going to be cosine of kx minus omega t, kx prime. But now I can drop the x prime because that is just, I was just doing that trick to show you how to write down the expression for a moving wave. This is the expression for a moving wave, right? Okay. Now, one thing that you might say, you might object to is the fact that I use the Galilean transformation, and you might say that, well, why am I not using the Lorentz transformation, right? So I can use the Lorentz transformation. If I use the Lorentz transformation, what happens? I get x prime is equal to x plus v naught t times gamma, right? So that means ax prime. So using the Lorentz transformation instead of Galilean one, what happens to ax prime? What is x? X is equal to x prime minus v naught t, and well, I should put a t prime here, x minus t prime. This is the inverse Lorentz transformation. So this means that a of x prime is equal to cosine of k of x is equal to cosine of k times x prime minus v naught t prime by gamma, which is equal to cosine kx prime by gamma minus v naught t prime by gamma, right? So now, according to this observer, what is the wavelength? Well, what is k prime? K prime is equal to k by gamma, right? And this becomes k times v naught. So lambda prime is equal to 2 pi by k prime, which is equal to gamma times 2 pi by k, which is equal to lambda times gamma. So now in this case, what you're getting is you're getting something which might seem odd, which is that the wavelength is dilated instead of being contracted. But that is just an artifact of the fact that I haven't really this is not really the way to go from one frame of reference to another frame. What I should do properly, right? Because the thing is, see, this wave is not really moving in the first frame of reference, right? In the first frame of reference, it's frozen. So if I want to go from one frame to another frame, what I should do properly is I should write down this thing, a moving wave in the original frame, then transform it according to Lorentz transformation. But the point remains the same. The point is that you still get a moving wave. You just get a moving wave with a different wavelength and different frequency. The form of this wave remains the same. It becomes k prime x prime minus omega prime t prime. So it has the same form, kx minus omega t, right? Kx minus omega t. The difference is that, well, the k prime and omega prime are changed, but the form of the moving wave remains the same, right? So the form of the moving wave, regardless of which frame of reference you are in, will always be a of xt is equal to some a naught, because there can be an amplitude also, times kx minus omega t. So this is a moving wave, okay? So here, when I talked about this electric field, right, I wrote it down in this way, that the electric field, right, this wave is something, some vector E naught times Z times cosine kx. So now I want to say that I have a moving electromagnetic wave. So I can do that now. So now coming back to electromagnetic waves. The form of a moving electromagnetic wave, I can write it like this: E naught Z cosine kx minus omega t. This is a wave which has a wavelength equal to 2 pi by k, which has a frequency equal to 2 pi omega, and which has a velocity. It is moving with some velocity. Now, what is the velocity of this wave? The velocity of this wave is going to be equal to lambda f, that is equal to omega by k. And what is omega by k? It has to be equal to c, right? The speed of light. So this is an oscillating electromagnetic wave. Now, if you look at a wave like this, what does an observer see? So we come back to this observer. Where is that observer? This observer. Now, what does this observer see? This observer sees this. Let's say this observer has a detector which measures the electric field. Okay. So it's no longer frozen in time. It is moving to the right with some speed omega by k. what does this observer see? This observer, now we say that let us put a detector in this observer's hand. Okay. And that detector measures the electric field at this location. What does this observer measure? This observer will find that the electric field E of T, right? What is this? This is the electric field at the observer's location, meaning at a single fixed point in space. What is the electric field seen by the observer? The electric field seen by the observer will also be something that is oscillating, right? But now it's oscillating as a function of time. This is the important thing to remember. Right? And this quantity is going to be the time period, capital T. Right? And what is the relationship between capital T and omega? Capital T will be equal to 2 pi by omega. Exactly by the same reasoning that you get for the wavelength, and K, same thing applies to capital T and omega, because capital T, the time period, that is the wavelength of the wave in the time direction. So this observer sees a wave that is moving past, right? But now the thing is that, so why do I keep calling them electromagnetic waves? Why not just electric waves or magnetic waves? Can somebody give an answer to this question? Anybody have any suggestion?
Since the electric field is changing, it'll produce a magnetic field. And
because this will generate a magnetic field, right? And now we can try and understand what the direction of the magnetic field that is generated is going to be like. So again, we will look at this wave that is traveling in the z-axis. So I'll take this picture again, and we'll try to use this to understand what the direction of the generated magnetic field is going to be. Okay. So now you remember, well, what is the relationship? How do I calculate the magnet like this? Curl of B, right, is not equal to 0 for all of this. Equal to not minus plus mu naught d by dt. Now E is in the z-axis. E is along the z-axis, right? So when I calculate dE by dt, if I calculate dE by dt just by calculating the time derivative of this expression, what do I get? I get minus epsilon naught minus E naught times omega z hat sine kx minus omega t, right? So dE by dt is a vector which is also along the z-axis, right? So what can you tell me about the B field? So this means that curl of B, right, this guy is along the Z axis. So if curl of B points in the Z axis, what can you say about the B field? So I have the curl of some quantity, and the curl of some quantity is pointing in this along this direction. What can you say about the vector field whose curl I'm taking?
Concentric, like the circles.
Right, but what can you say about the direction?
Perpendicular.
It has to lie in the plane that is perpendicular to this direction of the curl, right? So which implies that B has to lie in the XY plane, right? Because if this vector is dE by dt, then the vector field B has to lie in the XY plane, like this, right? Now what happens to dE by dt? Okay, and now we can calculate what this magnetic field should be. How do we do that? Again, we look at a fixed point, right? So we have the same picture as before. So I'll just copy a small portion of this. I have the same picture as before along the x-axis. This is the z-axis. This is the y-axis. Okay. Now I make a loop. I make a loop which lies in the xy plane because the magnetic field lies in the xy plane, right? So I make a loop in the xy plane. What does the loop look like? It looks like this, let's say. This is a closed loop, okay? Let me put some orientation on it. This is a closed loop. In the XY plane, okay? Why do I need a closed loop? Anybody? What is the purpose of this closed loop? How is it going to help me calculate the magnetic field?
Ampere's law.
Huh?
By using Ampere's law, magnetic field.
By using Ampere's law, well, and what? Which theorem? There is a certain theorem, right?
Stokes.
Huh?
Which Stokes?
Stokes theorem, right? Or Stokes law. I would use Stokes law. So how would I use Stokes law? This is my boundary C. I will call this curve C. And there is a surface. This is a surface, right? The loop encloses some surface in the XY plane. This surface I will call S. So the loop is C and the surface is S. Now, what does Stokes theorem tell me? Stokes theorem tells me that if I take the integral of curl of B, the flux of this through the surface S, and I don't put a circle here. Why not? Because S is not a closed surface, okay? This is equal to, by Stokes theorem, this is equal to the integral around the boundary, which is C. And now C is a closed loop, right? So I put a circle here, is equal to B dot dl around this closed loop. And this is equal to integral of of mu naught epsilon naught dE by dt dotted with dA, right? By using the right hand side of this equation. This is Maxwell's equation. By using the right hand side, because if I take the left hand side and I find the flux, that gives me the right hand side. I have to find the flux of the right hand side also, right? So now I have this electric field which is perpendicular to this loop, right? So there is some flux of the electric field through the perpendicular to the loop. And what I do is I make the loop really small so that the electric field is not really changing as I go along the direction of the loop. Okay. So if I make the loop really small, I can take the electric field to be approximately constant in space. And what is the magnitude of the electric field? What is the magnitude of this quantity? The magnitude of this quantity will be, well, I already calculated this. This is going to be equal to minus E naught omega Z cosine kx minus omega t, right? And now I'm saying that x is equal to x naught and t is equal to t. Well, and t is not fixed, t is changing. X is equal to x naught. What is x naught? I will take x naught to be this point at the center of this loop. Okay. So when I calculate the flux of this loop, what do I get? dA is also in the same direction. What is dA? dA is the area element times z hat. So if I take the flux of this quantity, if I take the dot product, what do I get? I get E naught omega, sorry, not cosine, sine. Did I write sine here? Yes, I wrote sine. Sine kx minus omega. Right? Now, the magnetic field can be in, let's say the magnetic field is going like this, B like this. Right? Then what will I get? I'll get B dot dl, approximately taking B to be a constant. B dot dl will just give me B dot 2 pi r, the length of that circle, the perimeter of that circle, right? So when I do this integral, what will I find for this B dot dl? I can approximately write it as B times the perimeter of that loop. Let me call it capital L. The total length of that loop. And this is equal to the area of the loop, right? When I integrate this, I will get dA, I will get the area times epsilon E naught times cosine times sine of kx naught minus omega t. Okay. Now in all of this, sine kx minus omega t, right? That is the end result. So what happens is that whenever I have a electric wave, that electric wave also generates a magnetic wave. So if I copy this again and I paste it over here, okay. So now what do I find? I find that there is also a magnetic field. Now I have done this calculation in a very rough manner, right? Because I have not taken the electric field at the different locations. I've assumed the electric field to be a constant. If you do the calculation in a proper manner, what you find is that the magnetic field points in the direction. So it lies in the XY plane, but it points only along the Y axis, not along the X axis. You find that the magnetic field looks like this. And also what you find is that here I've got a sine term, but it turns out that there is a phase factor of pi by 2 that I'm missing. When I include that phase factor of pi by 2, the sine term becomes a cosine term. So the magnetic field here is actually also behaving like a cosine, the same way as the electric field does. Like this. So this is what? This is my magnetic field. And this is what an electromagnetic wave looks like. This is a magnetic wave. And this whole thing is an electromagnetic wave. Okay. And actually, there is a very simple way to understand why the magnetic field is only along the y-axis and not along the x-axis. If you want to understand that, what you can do is, you look at the electric field here at this point, and you look at the electric field slightly away from this point, right? So this point is x, this point is x plus delta x. And now I draw the same loops that I drew earlier, right? I drew a loop like this in the xy plane for x, but I draw another loop over here in the xy plane for this point. Okay, no, this will not give me the answer that I'm looking for. Never mind. Never mind. I'm just trying to bring it, as I say, and I'm not doing a very good job. Never mind. Now, how do we get this electromagnetic wave? How do we get this solution? So far, I've just told you that E can be written in this way. I have not proven this fact, but now I can prove this fact by starting from these equations, starting from these two equations. Okay. So, can I have another 10 minutes if that's okay? Anybody have anywhere they need to go? Otherwise, if you don't mind, I'll continue. So now we consider these two equations. Curl of E is equal to minus dB by dt. And this equation, what we do is we take the curl of this equation. So on the right, we get curl of E. On the left, we get curl of E. On the right, I get d by dt, curl of P. And I explained to you in one of the previous classes that the order of the derivatives can be changed, because if you have something like this, partial derivatives commute, means I can change the order. And what is curl of B? Curl of B is equal to this expression. So that means I can write curl of E is equal to minus mu naught epsilon naught d by dt of dE by dt, which is equal to minus mu naught epsilon naught d by dt squared of E. And so I get this equation, curl of E is equal to minus mu naught epsilon naught d by dt square E. But this equation is also not very easy to solve. So what do I do? I use the vector identities I told you about. So remember that I had mentioned that there are some vector identities, right? This is a vector identity that I was talking about. So we have this quantity. And now instead of A, I put curl of C. Then what happens? I can write this as gradient of the divergence of C minus A dot B will become del square. It will become del dot del. So this quantity, curl of E can be written as gradient of the divergence of E minus del square E. This is the left hand side of this expression, and the right hand side becomes minus mu naught epsilon naught from here. Okay, now I have this equation, and what can I do with this equation? Well, in this equation, I have this quantity, divergence of E. Now, what is divergence of E equal to?
Potential.
Rho by epsilon naught.
Right?
Sorry.
But we are assuming that there are no sources, there are no charges. So we are in what you say is free space, right? We are in free space. So this quantity becomes 0. So I'm left with this equation, which is del square E is equal to mu naught epsilon naught dE by dt. Sorry. What is del square? Del square is del dot del. Okay. And what is del? Del is equal to I d by dx, j d by dy, k d by dz, right? So if I take del dot del, what do I get? I get d square by dx square, d square plus dy square, d square by dz square. This is called something by it's a Laplacian. That's the name for it, after some mathematician called Laplace. So when I write down now in this expression, you see you have a vector E and a vector E. So this is actually not one equation. This is 3 different equations for each component. So this I can write del square Ex is equal to mu naught epsilon naught. This is the X component. Then you will get the Y component and the Z component. Okay. All right. And each one of these x, y, and t, ex, ey, and t, they are functions of position and functions of time. Now I will make another simplification. I will say that my electric field is constant. It's zero. We will set this equal to these two is equal to 0. Why? So we'll say Ex is equal to Ey is equal to 0. So the electric field only has a Z component. Okay. Then we'll say one more thing. We'll say that the electric field, the Z component of the electric field, it only changes along the X direction. So if you look at this wave, right? If you look at this wave, the electric field only has a Z component, and the Z component is only changing along the X direction. So that means if I take this, the derivative of the Z component of the electric field along the Y or Z directions, it is 0. Okay. So finally, I'm left with this del square. Del square becomes what? It becomes d square by dx square Ez. Right? Because d by dy and t by dz are 0. And the right side becomes mu naught epsilon naught del square Ez by dt. This equation has the solution Ez is equal to E naught. You can write either sine or cosine, it doesn't matter. So I'll write cosine kx minus omega t, or sine, or a linear combination of sine plus cosine. So Ez is equal to E naught cosine this. Now let me plug this expression back into this equation. What do I get? On the right side, I will get minus k square Ez squared. On the left side, on the right side, I'll get minus mu naught omega square. Sorry, not Ez square, just Ez. And here I'll get Ez. Ez will cancel out, which will give me k square is equal to root of mu naught epsilon naught. Sorry, k is equal to omega, which tells me that omega by k is equal to 1 by mu naught epsilon naught square root, which is equal to, if you remember, we talked about this in one of our previous classes where I calculated 1 by epsilon naught mu naught. Do you remember what that was? I did this calculation in class, right?
Velocity of light.
Huh?
Velocity of light. C.
Sorry, no.
Velocity of light. C is equal to 1 by root of mu naught epsilon.
Right. No, so you can do this calculation. You can take the values of mu naught epsilon naught. This is equal to C is equal to 3 times 10 to the 8 meters per second squared. So the end result of all of this is that Maxwell's equations predict that you will have waves which move through space, and these waves will move at a speed which is given by the speed of light. Okay, so I'll stop here. I think this is enough material for one class, probably more than enough material. Okay. Yeah. All right. Questions? Any questions? Okay. All right, I'll stop the recording.